let's talk about homework from last class. When we talk about extreme values in mathematics, it really is super important that we get good at reading these graphs. And it sounds like such an easy concept, minimums and maximums, but then all of a sudden we get funky graphs like this and with holes and stuff like that. You're like, wait a minute, what is it that I'm looking for and why do I care? So for numbers 1, 2, and 3, we can have those conversations about absolute minimums and maximums. For number 2, if you're talking about this absolute max, it does not exist because it goes on forever and ever. And if you want to call that infinity, you're allowed. You won't get that wrong. So D and E does not exist, and infinity are both good answers for that. For this one, your absolute minimum, it does not exist. Does not exist because it's an open interval, first of all, and I can't quantify where this ends. So what I can say is I can get close, and snuggle up to it, but I'm never going to actually get there. And that goes back to that concept when we talk about Zeno's principle. He was a philosopher. And Zeno said, if I start on one end of the room and I leave the room half of the room at a time, am I ever getting out? So if I cover half the distance of the room, what's always left? So again, if I cover half of what was left, what's still left? If I cover half of what was left, what's still left? If I cover half of what's still left, and of course now I'm kind of confined by the size of my feet and the space, but if I cover half the distance, what's left? Half the distance, what's left? Half the distance, half the distance. So because I only cover half the distance, isn't there always something left? In mathematics, that's what we call the property of density, recognizing that infinity lives between 0 and 1. Infinity exists between every set of whole values. So if we look at number 2, as I'm approaching this here, am I ever going to get there? As I'm getting closer and closer and closer and closer and closer to this, I can talk about it as a limit of where I'm heading, but am I ever actually getting there? So that's why I can't say that there's a minimum. So if a lot of these conversations are confusing to you, maybe if you think about this whole being something I'm approaching but never actually getting to, that might make it easier. When we talk about absolute mins and maxes, that's the absolute highest point on the graph, the absolute lowest point on the graph. When we talk about relative or local minimums or maximums, we're talking about hills and valleys. If it's a hill, then everything, and you can see I created a little boundary here. When I look on either side of this, both points are lower than that maximum. So that's going to be a local maximum. And this here is my absolute minimum. And we can have an argument about whether or not this counts as a local minimum or not. Right now in the mathematics community, I think I told you this, they're very divided about what to call that. If you want to include it, you won't get it wrong, but if you leave it off, you're fine with that. Any questions on 1, 2, and 3 and things you want to talk about? Okay. Our next conversation is finding the critical points of functions. And as a review, a critical point is any place where my derivative is equal to 0, which means I'm encountering some kind of change in direction. When my derivative is equal to 0, I go from increasing to decreasing or decreasing to increasing depending on my function. And that becomes a critical point, a conversation for the function that we need to discuss. or if our critical point does not exist. Which graph up here, 1, 2, or 3, has a critical point where the derivative does not exist? 1, 2, or 3, where's the critical point with the derivative that does, where I cannot take the derivative? So 3 right here because it's a point, and 1, I can't take the derivative. I can take the derivative on specified intervals, but I couldn't take the derivative of this entire graph because it's not continuous. So when we talk about a graph being continuous, as a reminder, there's no asymptotes, holes, or jumps. If a graph is differentiable, it's continuous with no sharp points. Our critical points exist where my derivative is equal to 0 or on areas where I cannot take the derivative. Any questions on 4A or B? Are you okay with these comments, these conversations about restrictions, and these conversations about the value of the numerator? Do you understand why I really only care about the numerator equaling 0? Do you understand? It's going to be that kind of day.
Yeah.
Rainy, drab day. Good thing we're playing a game. I know. Good thing. Good thing she's got a game plan. Hey, a graph is increasing if the slope is positive, if the slope of the tangent line or the derivative is positive, decreasing if it's negative. Let's talk here. When we look at each of these graphs that show the functions, we can talk about where the graph is increasing or decreasing. And we can talk about where our critical points are. Questions on A or B? Number 7 and 8 is where we take a function, and in order to determine where it's increasing or decreasing, we find the critical points, and these sign charts end up being helpful because on either side of the critical points is where everything is changing. So it's my job then to figure out where the graph is increasing or decreasing by looking at the intervals on either side of the critical points. So here's where I worry. It's this whole thing here. The thing is mathematically obvious once you see it. If you're looking at somebody else's answers, you're like, yeah, that makes sense. Okay. And then when you have a blank piece of paper in front of you, and you do or do not do the homework, you do or do not put your brain into it, you do or do not see if you understand it or do your answers on your own, that determines whether or not you know what questions to ask or not. You done? Okay. All right, awesome. So hold on to those warm-ups. We're going to be talking about them in a little bit, but for now we're going to do some notes first. All right, so today's conversation is about using the first derivative sketch, which, surprise, you've already done. So what you're doing with your first derivative test was taking the derivative of a function, any function, or looking at the graph of a function, any function, and determining when the slope of the tangent line was equal to 0. So the first derivative test is taking the derivative, setting it equal to 0 to find those critical points, and then analyzing what is the graph doing on either side of those critical points where everything changes. So your first derivative test You've already done this. Use the first derivative to test whether or not a function has a maximum or a minimum by determining the critical points and analyzing the behavior on either side of the critical point. So with your group mates, will you please have a conversation about this graph addressing these questions on your market set talk. All right, come back. Let's talk about our graph. So it's a little bit hard to tell, so I'm okay with some estimations. We definitely have an end point here, and we definitely have an end point here. So if I needed to find my absolute minimum and maximum of my graphs coming across, it looks like 8.5. Did you have an absolute maximum at over 0? No, over 5-ish. And up 8.5. Typically in calculus, when we go ahead and we ask you what is the maximum, what we want mostly is that y value. So typically what we'll end up saying is the absolute max is 8.5 at x is equal to 5. So the shorthand to that is the x by ordered pair. But if you're answering something in the calculus way, a lot of times what they prefer is for you to state the absolute max is something at something. So we can talk about the same thing with our absolute minimum when we come back. This again looks like 8.5. Do you buy that? So the absolute minimum is negative 8.5 at x is equal to negative 5. All right, so our absolutes or our global, a lot of times. Did your algebra teachers ever use global or was it always absolute?
Absolute.
So the interesting thing is the word that goes with absolute is relative. So it's usually global, local, absolute, relative. But I like local because to me that references something that's not absolute but within the area of a different interval. So when I look here at this point here and this point here, I can see that the tangent lines at that place are going to be 0. So I can see that my graph goes from increasing here to decreasing here and back again to increasing here. So that change in my graph happens at these two local extrema, whether we talk about minimums or maximum. So my local minimum, what do you have that at? 0, 1, 2, 2.5? Minimum at over 2.5 and down 6. Do you like that? And here my local maximum is at over 2.5 in the negative direction. Oops, this is negative. And up 6. So when we describe the behavior of the graph of f of x around the local minimums and maximums, we're talking about the graph of f of x. Remember, this f of x represents my y values. So I'm talking about my output. So what is happening to my output in between each of these critical points? My absolute min and max and my local min and max. So we can say that my graph is increasing, and it's increasing from negative 5, an x value of negative 5, up to an x value of negative 2.5. I could say it's decreasing once it passes that negative 2.5, all the way up to a positive 2.5, and then it starts to increase again after 2.5 up to 5. So that's what we're talking about, that y value is the output. Now here's an interesting conversation. What is the output of this function? What am I asking for there? Yeah, the slope of the tangent line. I'm asking you for the behavior of the derivative. So if you want to, you can take one of your straight edges and put it on your graph, and you could take it up and around like a roller coaster ride, and you can look at what that tangent line looks like at all points of that graph. Because at any point, this ruler can represent your tangent line when you're looking at the slope of that tangent line and the first derivative of that function. So when we look at it, what is happening to my derivative as I approach here? Is it positive or is it negative? It's definitely positive. It's positive this whole way. And is it positive growing bigger or positive growing smaller? What is it doing? So from negative 5 up to negative 2.5, my f prime of x is positive, but it's decreasing. It's very steep here at the start, and as my tangent line approaches, it's getting less steep, 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 less steep. And what am I working my way towards? Yeah, it's decreasing as it's approaching 0. And once it hits that critical point, that slope of that tangent line is right there at 0. As it goes from negative 2.5 all the way to 2.5, what is happening to my tangent line? Is it positive or negative? It's negative. What is it doing? Yeah, it's increasing. Isn't it getting more and more negative? So the increasing, decreasing conversation is difficult because it's decreasing. So it's negative, and let's just say getting steeper. We could talk about the absolute value. And it's getting steeper until what? Right? Until it starts to change again, doesn't it? Getting steeper, and then it's going to approach 0 down here. Once we hit positive 2.5, and we move up to 5, what's happening to f of x? Yeah, it's positive, and we can say and increasing, because it keeps getting steeper and steeper and steeper. It's super important that you understand the telling of the story of the graph. And until you practice saying the words out loud and defending what you're saying by either the behavior of the graph, the derivative, the sign of the derivative, your output values, it takes some practice to getting used to. When we talk about your justification statements, what we want to do is we're going to make sure that we let everybody know why we know that there's a minimum value or there's a maximum value. So if we talk about a minimum value at x is equal to c, we can talk about because the derivative at f of c is equal to 0. If there's a minimum value, think about what that looks like on the graph. If there's a minimum value, that means that my derivative was this way and now it's this way. So we know it's a minimum value because the derivative is equal to 0 and changes from a negative to a positive value. So when we talk about what's happening to the derivative is negative, it changes to a positive value, therefore C is a minimum. So that justification, we need to make sure that we're saying it correctly. Talk to your group about how you would justify what a maximum value, how you would justify a maximum value. Go. All right, what did you write? Somebody tell me. What did you write, Grace?
That b equals 0.
Okay.
And that it's increasing, it's positive and then negative.
So because f of d is equal to 0 and go ahead.
It's positive value and then it goes to
Mm-hmm. And the sign changes from a positive to a negative value. So just so we're on the same page, if f of c does not exist, then it can't be a critical point. So we want to make sure we understand. And that comes from a lot of the restrictions that we get in a lot of our square root functions. Having that value under the radical be negative, can't do that. If we have a rational function where we have a value that gives me 0 in the denominator, can't be that. So if f of c does not exist, then x equals c cannot be a critical point. All right, so let's go ahead and use the first derivative test to find the x values of any relative extrema and use our first derivative. So the first thing we're going to do is take our derivative, f prime of x, 3x squared minus 12. Everybody okay with that? When I set that equal to 0, I'm going to factor out a 3, and I'm going to get something that's very familiar. And I get x is equal to positive 2 and negative 2. Did I skip too many steps? You okay with that? I factored out a 3, divided side by 3. I went ahead and called this x plus 2 and x minus 2. And then that's how I got those x values. All right, so here's our story. Our x values go from negative infinity up to negative 2. Then at negative 2, my derivative is 0. Then my x values go from negative 2 to positive 2. Then at positive 2, my derivative is equal to 0. Then my x values go from positive 2 to infinity. Are we okay with that? Anything I need to go over? Any questions? Where did that come from? How'd you get that? Do you understand why these intervals are there and where I got them? Now, we kind of cheat and put that box in there for you to draw out for as many intervals as you need, for as many critical points as you need, so that you can go ahead and talk about. All right, so with your group mates, go ahead and pick some test points and tell me whether the sign of my derivative is positive or negative in each of those intervals. Turn and talk it out. Go.
Let's do negative.
No. Negative.
So here's the interesting part of this conversation that I need to make sure you understand. Because my derivative, and I need to make sure I have my derivative here, because the value of my derivative at each of these things, each of these intervals is positive and negative, and then positive again, I can go back and look at what my graph must be doing. So from negative infinity up until 2, my graph is increasing. So I can say it's increasing. Then it hits this critical point where it starts to be decreasing. And then it hits this critical point where it starts to increase again. So I know that my original function is a cubic because I can look at where my graph is increasing and decreasing, and I know then that this critical point is going to be a local maximum, and I know that this critical point is going to be a local minimum because of the way that the signs are changing as I go. So we're going to get to a point where we can make predictions for what our graph is doing just by looking at these different conversations that happen as a result. So my graph was x cubed minus 12x plus 1. So when I look at my graph, maybe I need to zoom out a little bit. I can see it's going to follow that cubic path by going up, and then once it hits that critical point, here's a local maximum, here's a local minimum, and that tells me which ones they are because I look at the way that the signs are changing up here. Make sense? Go ahead.
For the middle one, the decreasing part, how do you know it's decreasing?
Because my sign of my tangent goes from positive to negative. So because my tangent line goes up, so think about my tangent line here. It's increasing here. It's 0, and it's because the slope of my tangent line is negative, I know that I'm going back down. Make sense? Okay. So when we have the first derivative test, you can find things. Now, we start you off with quadratics and cubics because that's a lot easier. But now we have this lovely. with your partners, go ahead and figure out where our critical points are. On your market set, go. Have a critical point if that derivative does not exist at that point. So when we go back and we look at this graph, my denominator cannot be equal to 0. So x cannot equal 2, 2 and negative 2. So we don't count them as our critical points. You okay with that conversation?
Yes.
Okay. So instead what we do is we look at where is our numerator equal to 0 in our derivative function, and that's at 0, so that's critical point. So we test what happens on either side. So what is interesting is instead of looking at just that very local behavior, because we've got a mess here with these undefined restricted, what we want to know is all of our extrema, like what is the graph doing long term? So we introduced this concept to you of substituting in infinity, which you're like, wait, what? Yeah, infinity is an idea, not necessarily a value. So if I'm plugging in any negative number in my denominator, that negative number is going to square away. So I end up with a negative value over a positive value. So basically, I end up with a decreasing function as it continues going on forever and ever. That same idea, that positive value stays positive, and then I end up with an increasing function as my graph goes on forever and ever. So if you're curious about what to do about all of that middle stuff, here's the story of where those asymptotes are. And as I'm talking about this part here, because my graph is decreasing, this represents, right before there, a local maximum, because the points on it are smaller on either side. Here's a local minimum because these points are on either side. If we were to look at this function as a whole and go back and look at what does this function look like as a picture, we have x squared minus 4, oops, I hate when I do that, x squared minus 4, and that's all to the 2 divided by 3 power. So when we look at, here's our graph, and that's what we can understand, where we have, what is the sign of our derivative? It's positive. And we get to kind of just ignore this part of the middle, because long term, what's my graph doing as it moves on? Is that okay? Okay. So now what we want to do is talk about examining the behavior from the graph of f of x. And this is going to stretch your mind a little bit, because what we want to do is we want to talk about determine the intervals where f is increasing and decreasing based on the graph of f of x. So here's something to really keep in mind. Ready? You're talking about f of x. Its derivative. You're talking about f of x's derivative. So if we want to know where the function is increasing and decreasing, we have basic conversations with ourselves about whether things are increasing and decreasing. And it goes like this. Anytime that my derivative is positive, that means my function is increasing. Anytime that my derivative is negative, that means my function is decreasing. So with your group mates, have a conversation. If this is the graph of the derivative, determine the intervals of the original function where it's increasing and decreasing. Go ahead, turn and talk. All right. So do you see the fact that here, because this is my graph of my velocity, graph of my derivative, could be the velocity. If it's positive, my graph is increasing because my derivative is positive from negative infinity up to, what does that look like, -3? What happens once it drops down here? What happens? It's decreasing because my derivative is negative from -3 up to 1. And then what happens once it comes up above? What happens? My derivative is positive, so from 1 to 3, it's increasing. And then from 3 to infinity, the derivative is negative, so it's decreasing. So if we wanted to, we could look at and try to think about, okay, what would my original function look like? If we wanted to stop and think about what my original function might look like, I know that here my graph is decreasing, and at this point here my velocity changes, or my second derivative changes. It hits 0 and then it starts going negative. So if we talk about my graph increasing at a decreasing rate, that's going to be one of those kind of curves. When my slope of my tangent line, when my derivative is equal to 0, that's where I have that tangent equal to 0, and it flattens out. Now this is interesting because my graph by first derivative is negative, so it's coming down. And then I have a couple of these times when my graph is still decreasing. It's still decreasing, but it's decreasing at an increasing and decreasing rate. So around this point is where again I have that minimum because the graph of my tangent line is equal to 0. And I have a positive velocity. And my positive velocity means I'm increasing, but I'm increasing at a decreasing rate until I again bottom out. And I end up having a negative velocity again. So if you're chatting with your friends through while I'm talking, number one, you're being rude. And number two, you might want to tune into what it is that I'm doing. Because I'm talking myself through what this graph means. I'm looking at the derivative. And I know that when my derivative is positive, my graph is increasing. And that's the hardest part to start with. Here my derivative is positive. Here my graph might be negative. But I'm increasing. Every time that my derivative is equal to 0, that's a critical point. That's a critical point. And that's where my graph changes from increasing to decreasing because the sign of my derivative changes. My derivative is positive, my derivative is negative, my derivative is positive, my derivative is negative. Now here's a really interesting thing. Are you surprised that your graph is a quartic graph? Because your derivative graph is a cubic. So doesn't it make sense that the derivative graph would be 1 power less than my original graph? Right. So here's this next exercise that we're going to do. And these graphs are super light, so I want you to either grab one of the colored pencils from the basket? Because I want you to go ahead and trace over what you see. And I'll ask you again to not talk while I am. So if you trace over these graphs, what you're going to be doing is justifying the behavior of the original graph with what you're seeing happening with its derivative. And you're going to be matching up which graph by looking at the critical points. So let's go ahead and just talk about our original functions for a minute. Anytime I have a relative min or a relative max, that's a time when I have a derivative equal to 0. So that's when I have a slope of my tangent line is equal to 0. Can I take the derivative of a point? So this is where my derivative does not exist. As you look at each function, talk to yourself about whether the function is decreasing or increasing along its path of x's. Pay attention to local mins and local maximums. So we'll go ahead and call these graphs 1 and 2 and 3 and 4. And you can go ahead and match them up with A and B and C and D. Go ahead, talk with your groups. Go. All right, let's come back. There's a couple features about each of these graphs that are dead giveaways. Who thinks they have one? Go ahead, Grace, what do you think?
2 and C.
So you think 2 is C. How come?
Just because it's the only one that is D and E and it's only
Yeah. So when we talk about 2 matching up with C, here is where we have that derivative not existing, right? And then here we have not being able to take the derivative. Let's talk about this though. Let's keep talking about C. Do you see how C's graph is a constant rate of change?
Yes.
Do you see how here we have a constant rate of change on our slope? And isn't that a positive increasing? And isn't this a positive increasing? So here's our positive, here's our positive. And then check this out. That's our negative in between. So 2 and C is dead on. I love it. Thanks, Grace. Who else has a guaranteed that they know? Guaranteed that you know. Go ahead, Catherine, what do you think? 1 is definitely A. How come?
Because of the original function, there's 2 derivatives where it's 0 and the derivative drops.
I'm sorry, there's like people talking between you and me, and I can't hear what you're saying. So I'm gonna have to ask you to start over. Go ahead.
On the original function, there's 2 tangent lines where the slope is 0 and on the derivative graph there's 2 zeros.
Yeah, so check this out. Here's these 2 places where the derivative is equal to 0, and there it is. Those are those 2 places where the derivative is equal to 0. Talk to me about what kind of graph this is. Linear, quadratic, cubic, quartic. What's the graph of its derivative? It's quadratic. Isn't it one level less? Doesn't that make sense? How about the whole conversation about, here it is, my slope of my tangent line, decreasing, increasing, decreasing. Here's my slope of my tangent line is negative, positive, and negative. All right, 1 and 2 done. Who else has a conversation for me about what they know?
4 and B because
4 and B, keep going.
for the same reason as 1 and
So
because like the thing.
I love it. Here's where my derivative is equal to 0. Here, here, here. Here I have a or a quartic. Here I have a cubic, one level less. Here I have my derivative. My function is increasing. My function is decreasing, increasing, decreasing, which means I start with a positive derivative. Then I have a negative here. Then I have a positive derivative. And there I have a negative. So 3 and D are the tricky matchups here. 3 and D. Would you talk to your group mates about what you see happening here and why you think that this one is what it is? Go.
I think because